Okay, so I have here just some x's that we can use to graph this function. And what we're going to do is we're just going to take each of these x's and input them in for the exponent here. And then making sure that we're following BEDMAS. So we'll do like half to the exponent -2 and then multiply that by 4. So I'm going to give you guys a second. We're going to enter each of these in for each of these x's here and record what we get for the y values. Okay, so everyone should have calculators out and should be calculating. I'm going to give you a couple minutes to do that. Okay, so you should have gotten these values. So when we think about graphing this, I think maybe we just won't graph this specific point here, but we'll graph the rest of them. So let's just take a second and plot those points. And if we imagine continuing to half this, really our graph isn't actually going to ever hit 0, right? Like if I keep going here and I keep halving and halving and halving, my decimals are just going to get smaller and smaller and smaller, but they'll never hit 0. So really, I actually have like a horizontal asymptote that emerges here at y = 0. So we'll put that in for asymptote and then just sort of draw our graph so that it's not crossing over that asymptote, but it's just approaching the asymptote. Okay, so when we think about domain here, this is going forever toward the right. And it's also getting wider toward the left forever as well. So there's no restrictions on the domain of this function. However, for the range, we only want positive values, and we don't want our range to be equal to 0 either. So we're going to say all real numbers, but y must be greater than but not equal to 0 because it can't cross or touch the asymptote here. So all positive values greater than 0. In this case, because we have this asymptote along the x-axis, there's actually no x-intercept. And then for our y-intercept here, we can see it's at 0, 4, or you can look at the graph as well. And then intervals of increase, decrease. So we haven't done this before, but for exponential functions, they're either always increasing or always decreasing. So in this case, the way that we can tell, or in all cases, I should say, the way that we can tell is we will start at the very left of the graph and we will drag our pencil toward the right, and we want to pay attention to whether our pencil is going down or going up. So if I start at the left of my graph here and I travel toward the right, my pencil is actually going down, and that actually means that I have basically the whole interval is an interval of decrease. The graph is decreasing everywhere. So we would say in this case, we have no interval of increase. But our entire decreasing interval is essentially the entire graph. So the graph is decreasing all the way from -infinity to +infinity. So essentially what I'm saying, this is not an xy coordinate. Of course, I can't have an xy coordinate that is -infinity, +infinity. Basically what this is saying is the y's are decreasing from -infinity, or maybe I should say as x goes, from -infinity to +infinity. Or left to right, basically. As we travel left to right, the graph is decreasing everywhere. Okay. So here's our next one. When you enter in your x's here, so just be mindful, there's already a negative here. So when I enter in -2, I'm going to have -2, and that will become positive. Also, there is a difference in this case between -3 to the exponent -x and -3 to the exponent -x. What is to the exponent of -x is just the 3. So you can almost imagine that this is almost like -1 times 3 to the exponent negative x. So after you raise 3 to your exponent of negative x, as you enter these in, you will multiply by negative 1. Okay, so I'm just going to give you guys a second to enter those in and see what you get for y. Okay, and then let's plot our points. And maybe we'll just switch these to the other side. Okay, so if we kind of imagine what the shape is sort of going to look like here as we connect these, it's always just going to be like a nice smooth curve, like so. And then on this side, if we keep going here, this is just going to do kind of what the other graph did, which is like get closer and closer and closer to 0, but it's never going to touch the x-axis. So again, we have this horizontal asymptote lying along y equals 0, or in other words, the x-axis. So you can fill that in for asymptote down here. Okay, so any thoughts on domain for this one?
And then just x equals all real numbers, like the same thing.
Yep, it is. So this is going to be true for basically every exponential function that you have. There's no restrictions on x. I can sub in, if we think about the equation of this, I can sub in whatever I want for x. There's no restrictions on what I can put in for an exponent. I can put in a fraction, I can put in a negative, I can put in 0, I can put in a positive, a decimal, anything. So my domain is all real numbers. It's always going to extend in both directions forever. Okay, how about range? Can someone create our range expression here?
It's y equals all real numbers that are less than 0.
Okay, so y must be less than 0. All right, in this case, again, because we have this asymptote along the x-axis, there's no x-intercept. And we can see our y-intercept right here. It's at 0, -1. Okay, so as I said before, when we do intervals of increase, decrease, we are going to start at the left side of the graph and just drag our pen along the graph toward the right. And we're going to pay attention to whether our pen is going up or whether it's going down. So in this case, if you notice, as we bring our pencil along our graph from left to right, our pencil is moving up. So we have only intervals of increase here. So there's no interval of decrease. And we would basically just say that the graph is increasing everywhere. So our interval of increase is just from -infinity to +infinity, just like we had for decrease last time. So literally we're just saying everywhere the graph is increasing. And then there's no interval of decrease because there's no area where our graph starts decreasing. Okay, so this will always be true for exponential functions. You will have one, either increase or decrease, that's going from -infinity to +infinity, depending on what's happening in your graph. And the other one you will not have an interval for because all of these graphs are either always increasing or always decreasing.
How do you check again if it's increase or decrease?
So just take your pencil, start at the very left of your graph and move your pencil toward the right and watch whether your pencil is going up or whether your pencil is going down as you move left to right. If you're going up, then you're increasing. If you're going down, then you're decreasing. Okay, any other questions for this one before we move forward? Okay. All right, we are going to determine the equation of the exponential graph in the form y equals a times b to the x. Our goal here when we're creating an equation based on a graph is to have a plugged in and to have b plugged in. So a is sort of like the initial value. A is going to kind of be like, where do we start when x equals 0? It's going to end up being sort of like the y-intercept when there's no transformations or anything like that. Now, in this case, this is pretty hard to see because it's not really crossing on an exact cross section. But perhaps if we find a couple more points, then that will help us. So I'm just going to create a table of values, and then I'm going to mark off some points that I can actually see on here. So I see the point, I'm going to leave a little space here, but I see the point 1, 6. I also see the point 2, 18. And then I see the point 3, 54. Okay, so basically the b value is going to be what is the multiple for me to get from one y to the next y. So is there something consistent that I'm multiplying these by to get the next y coordinate? Ben?
3.
Yeah, so if we notice we times 3 and times 3, we can continue to generate more points. This means that b equals 3. Okay, in other words, our y's are tripling, right? It's kind of like our exponential growth questions where we have things that are tripling. So could I figure out what this y-intercept is if I went backwards to 0 here? If I'm going backwards, I'm not multiplying by 3, I'm dividing by 3. So my y-intercept should be 0, 2. This is the a value. Okay, so here a equals 2. Remember, this is initial value, right? So that's going to be like our y-intercept. So you're just going to sub that in. You'll have 2 for a and 3 for b. And that's your formula. Or equation, I should say, not formula. Okay, so figure out what your multiple is to get from one y to the next y, and then figure out what that y-intercept is. That's going to be your a value. Any questions before I move forward? Okay. So there's a bit of a summary that we can sort of create, and we can know the shape of our graph just by looking at the equation y equals a times b to the x. So I can predict whether my graph is going to be increasing, I can predict whether it's going to be decreasing, and I also will know whether it's above the x-axis or below the x-axis based on what my a and b values are. So these are probably the most straightforward graphs because we talked about growth and decay. So this would be like exponential growth when b is greater than 1. And this would be like exponential decay when b is in between 0 and 1. So for instance, our half-life questions when b is equal to a half take on this form of a graph. And both of these cases are going to be when a is greater than 0, or in other words, a is positive. Okay, so perhaps an example of this type of graph could be any positive a value. So let's just say a was 5, and then a b value that's greater than 1. So let's say 3, for instance. And then this one is going to be the same idea for a. So let's just say maybe for a, it's 5. And for b, it needs to be a value between 0 and 1. So perhaps maybe it's like a half or something like that. Okay, these are just samples of something that could produce this type of graph. Now, the bottom ones here, you'll notice that the b's are actually the same. So growth and decay, except the a is now negative. So what's happened to our graph above is it's actually just been flipped down vertically. So I really usually only remember the first two options, and then I just remember, oh, if A is negative, then those graphs are vertically flipped upside down. And then we will have kind of the opposite of what was happening before. So growth, when A is positive, increases, but when A is negative, it gets flipped upside down and it becomes a decreasing graph. So an example could be literally exactly what we have above, but just making A negative is going to cause that graph to vertically flip. And then it will become a decreasing graph. And then same thing here. So an example of this one would be literally the exact same thing here, except we just make A negative, and that causes a vertical reflection to happen. So we're going to take a look at just creating like really quick sketches of graphs based on whether A is positive and B is greater than 1, or in between 0 and 1, or whether A is negative, that kind of idea. Just so we can start to understand what the equation does once we change the A and B values. So if we're just creating a really basic sketch, all exponential functions, if they don't have any like plus or minus on the end, like let's say this was +7, that's a vertical translation, up 7. But if they don't have anything like that, like -1 or anything like that, they're all going to have a horizontal asymptote at y equals 0. Okay, even this one as well, we can put that in already. And then we are going to identify the Y-intercept, which is essentially, again, if we don't have any vertical translation or anything like that, it's going to be the A value. So in our case, the Y-intercept is 0, 2. And then you're going to decide on a shape. So the only real options are it can be above and it can be growth. It can be above and decay, or it can be the flipped versions of those, which will only happen if A is negative. So in this case, this is either going to be based on the B value. Will this be growth or will this be decay?
It'll be decay.
It would be decay, yes. That's because B is between 0 and 1. So that must be, this must be above the asymptote. And kind of going downward. So we're going to plot the Y-intercept at 0, 2, and then just like kind of pencil in the general shape of this graph. This is just like a basic sketch. Okay, so I know that this one also is above the asymptote. Okay, but this time B is greater than 1. So this must be growth that's happening. Okay, so if we identify, so we have our horizontal asymptote, it's at y equals 0. We'll identify the Y-intercept and plot it. That's going to happen at the A value, so 0, 2. And then you're going to decide on the general shape of the graph. So in our case, our shape should be, once we plot the Y-intercept, should be above the axis and growing. Something like this. Again, this is just like a very basic sketch. All right, so I'm noticing for these ones that A is negative. So these must be below the asymptote. This is a vertical reflection.
Can you go back for just like 1 second?
Yep. Good?
Yeah, good, thanks.
No problem. So when A is negative, this is a vertical reflection. So think like this one should be one of the ones that's below the asymptote. And this is where B is greater than 1. So this should fall into the general shape where A is negative and B is greater than 1. So it should look like this afterwards. And then we're going to identify the asymptote, which is always at y equals 0 if you don't have a vertical shift, which in these cases we don't. And then you're going to identify the y-intercept and then the general shape. So the y-intercept is going to be -2. Again, because there's no horizontal shift or vertical shift here. It's just the a value. So I'm going to plot that down at -2. And we said that it should take on essentially the shape of growth flipped vertically. So it will end up actually being a decreasing graph. So it should look like this. Something like that. Okay, and then always make sure that you're sort of drawing your graph so that it's like curving around your horizontal asymptote here. And shouldn't be crossing your horizontal asymptote either. Okay, and then finally here we have a is less than 0 or negative, and we have a b value between 0 and 1. Horizontal asymptote, there's no vertical or any kind of shift or anything like that, so it's still going to be at y equals 0. So we'll just pencil that in. Y-intercept should be at the a value. Again, no horizontal or vertical shifts, so we'll plot that. And then this should kind of look like the graph of decay, but flipped upside down. So if you imagine that happening, it's going to end up actually being an increasing graph when we make a negative. So that should be the shape of our graph. These are the only 4 options of what you're going to have for the basic shape of an exponential function. Now, of course, once we start adding in like vertical shifts, these things can kind of like shift up and down as well. But in general, all exponential functions are going to have this basic shape, right? They'll always kind of go off to one side and then curve toward the horizontal asymptote. And then you just need to decide whether it's above or below the horizontal asymptote and what kind of general shape it takes on. Any questions? Okay, so we're gonna kind of pause here for a little bit